Hi, you're listening to Avril Sauter, and we're talking about CCNA wireless. In this lesson, we're going to be talking about wireless networks. Those different wireless networks, what are the industry terms that are used when we define those networks, and then we're going to talk about how they work, because at the very heart of wireless, all of the wireless networks work the same way. The way they've been implemented is different, and so they have different applications, but the fundamentals of wireless remain the same, whether you're talking about your wireless LAN connection or your cellular phone connection. So in this first part, I want to give you the industry definitions for the different types of wireless networks. Now in this graph, we're giving you the different terms that are used, and you'll see the circles or the ovals that are in the middle. Those are really defining coverage. And so for a personal area network, we're talking about things that are in your close proximity, that are close to you. Things like between your cell phone and your earpiece. That would be an example of a wireless personal area network. If we extend the range a little bit more, then we come out to the wireless local area network. And wireless local area networks, for instance, you may have a Wi-Fi access point deployed in your home that gives you coverage within your home. Then we talk about wireless metropolitan area networks. So this is where we're going outside of the home. We're perhaps covering the city area or a local town. Example technologies here would be WiMAX. WiMAX was a technology that Cisco invested in for many years. Then if we go further out, we talk about things called the wireless wide area networks. And this is really where you'd start thinking about your cellular networks. Your cellular networks are effectively nationwide. There's a few places in the States where the terrain is rather prohibitive that you won't actually get coverage. But in the areas where people are, in the city areas, in the rural communities, they all have cellular coverage, and so it's known as a wide area network. And if you're not familiar with the cellular technologies, there'd be things like GSM, GPRS, which is data over GSM, UMTS, which is your 3G networks, or maybe even LTE, which are your 4G networks that are rolling out. So let's step through each of these different types of network. The first one here is the wireless personal area network, the PAN. Again, as I mentioned, close proximity, so normally between 20 and 50 feet. Sometimes the technology is just a one-to-one relationship, like between a gaming console and display screen. Other times it can actually form a small network. So for instance, Bluetooth is capable of forming a small piconet, and you can have up to 8 active devices communicating with one another. They may or may not be standardized. So they may follow a standard like 802.15, or they may be a proprietary standard. 802.15 actually encompasses many different wireless personal area network standards. So Bluetooth is covered under that. The Zigbee wireless sensoring network is also covered under that standard. So it's not just one standard, it's actually a multitude of different radio standards covered in the IEEE 802.15. So then we have the wireless local area networks, which of course the wireless LANs is where we're going to focus our attention to in this course, and they have better coverage. You're going wider than the personal area network, up to about 100 meters. If you think in metric terms, if you're thinking in feet and inches, then that would be 200 to 400 feet is normally what you'd expect with a wireless local area network. The difference here is that you're not just connecting one person's personal devices, but you may have several people that are connecting And so as this illustration shows here, I've got several different computers connecting to a wireless access point. With a personal area network, they're really sharing data between the different devices. When you start thinking of a wireless LAN, you typically also think about connecting to the corporate network, connecting to the internet. And so multiple people connecting through and forming a wireless network. 802.11 is the dominant standard in wireless LANs, and it uses a modulation techniques called direct sequence spread spectrum and orthogonal frequency division multiplexing, and we'll be talking more about those later on. But whenever you want to get up to really high data rates, you want to be using an OFDM radio. When you're doing something like low data rates like sensoring networks, then using a direct sequence spread spectrum radio makes a lot more sense because it's a lower cost, cheaper radio. And the last comment on this slide is that the behavior is kind of bursty in behavior. And what that means is that you have multiple devices sharing a radio resource. And so we're going to take turns. I'll send some data, then you'll send some data. So we're going to take turns in using it. And so our transmissions tend to be bursty as opposed to continuing 100% of the time. So metropolitan area, the range does vary quite a bit, but you'd normally expect a metropolitan area to be covering the metropolitan area, as the name suggests. When we look at wireless LANs, quite often those are placed on the ceiling, 10, 20 feet high. When you start looking at metropolitan area networks, you're looking at potentially transmission towers. They're deployed much higher up. And that's what really enables them to get much higher coverage. And they're deployed in frequency bands that allow a higher transmitted power. And so, the 3.5 in this country, overseas you might see somewhere between 3.3 and the 3.6. You'll see it in the 2.5 gigahertz band in this country. And when I say this country, I'm talking about North America. And then you also see the 5.8 gigahertz band. And this is deployed outside. The regulation is a little bit different outside. They can get up to higher power levels, which means their signals are going to go further, which means their coverage is greater. If it's a technology which is focused on providing high-speed data, you're going to see an OFDM radio. And 802.16, which most people refer to as WiMAX, is an OFDM-based technology. With WiMAX and the frequencies it's deployed at, can be deployed for line of sight, backhaul kind of requirements, but is typically deployed in a non-line of sight environment, much like cellular is deployed, where you put up one tower and then it provides coverage all the way around the tower in order for people to connect. And then you have the wireless wide area network, and this is when it goes out of the metropolitan areas where you have the dominant number of people, and it goes now into suburban areas, into rural areas, along highways that are connecting towns and cities. Now, in the cellular networks, in the city areas, you'll have small cells that will be perhaps less than half a mile, but out in the rural areas and along highways, cellular towers are normally anything up to 20, maybe 25 miles. If you're thinking kilometers, maybe about 35 kilometers. So they're much larger towers out in the rural and along the highways in order to maximize the coverage. The frequencies can vary. If you're cellular, you'll be down at the 700, 800, 900 megahertz, maybe the 1.8, 1.9 gigahertz. You can also deploy it at higher frequencies as well. Now, cellular technologies like GSM and GPRS are based on what we call a time division multiple access, TDMA. Older technologies were based on TDMA, and so those technologies, as we move away from voice into high-speed data, are transitioning out. And so you see the transition from GSM 2G technologies, which are TDMA, to CDMA, which is 3G. CDMA is code division multiple access, where now I'm using codes to distinguish between my different uses on the network. But again, as I mentioned before, as cellular is migrating to higher and higher speeds, when we now look at cellular 4G technologies, they've all moved to OFDM, orthogonal frequency division multiplexing. And again, that is the area interface of choice if you're doing high data rates, and it doesn't matter whether you're talking about a personal area network, a wide area network, a metropolitan area network, or a wide area network. If you're doing higher data rates, you want to be moving to an OFDM radio. The last comment here about the behaviors lower data rates, that's really in comparison with wireless LANs and metropolitan area networks. So if you get up to a really big cell, you've got a lot of users sharing that spectrum, and the data rates per user will be lower, and also simply because you've got wider coverage, your data rates will be lower, and I'll talk a little bit more about that in a moment. So we're going to start focusing in on wireless LANs, but I did want to share with you an example of another technology, and in this case I actually chose a wireless personal area network and something called Zigbee. Now the Zigbee standard is defined by the Zigbee Alliance, but as I mentioned earlier, it's also been incorporated into the 802.15 standards group, and it's actually called 802.15.4 as indicated on this slide. Zigbee is used for a lot of sensoring equipment, and so you can have a home controller and then you can have your different devices connected wirelessly in your home, and they're using this Zigbee standard. So here's an example of a technology which operates in the same frequency as our wireless LANs, and we have to coexist with, but it's very, very different. So now we get to talk about modulation, and I love talking about modulation. I've been teaching at Cisco since the late 90s, and so I've taught a range of RF engineers to software engineers to product marketing. And a couple of years ago, one of the really technical architects came up to me and said, you know, I've had people explain modulation to me maybe 20 times, different instructors, and I've never understood it until Avril, you explained it. So I'm really hoping that this will be easy for you to understand as well. So the technical way we talk about it is we could say we're going to take your digital data and we're going to encode it onto a carrier signal. But the simple way of thinking about that is simply your ones and zeros represented in waveforms, because what goes out over the air is not ones and zeros, but is waveforms. And when we look at a waveform, we can vary the waveform in three ways. We can change the amplitude of the waveform, i.e. we can have a big wave or a little wave. We can change the frequency. When I talk about the frequency, I'm talking about the number of cycles per second, the number of times that waveform goes up and down per second. So I can slightly incrementally increase the frequency, slightly decrement it a bit, and I can distinguish between your ones and zeros. I can also change the phase of the wave as well. And so if I can change the waveform, different waveforms can represent different combination of ones and zeros. And it's really as simple as that. So let's take a closer look. Okay, so let's talk about amplitude. And here you can see I have a big wave here. I'm varying the amplitude, and now I'm sending a small wave. And so I can say, okay, this represents a 1 and this represents a 0. And so again, by changing the amplitude, which is the power of the waveform, I can distinguish between ones and zeros. Also, I can change the frequency. See how here these waveforms are going up and down, the number of cycles per second, each up and down is considered one cycle. So if I send less cycles per second, then that can represent a 1. And here, see how I'm going up and down a lot more, often per second. So there I say, okay, that's a 0. So I can change the amplitude, or I can change the frequency. the other thing I can do is change the phase. So here you can see I'm going up, and I can say, okay, if it starts with an up, is a 1, and if it was to start coming down here and then going up, I could say, oh, that's a 0. So I can change my amplitude, the frequency, and the phase to distinguish between your 1s and 0s. Now, what's really exciting here is not that I have to choose one or the other, I can actually combine them. And that's what we do on most modern radio that's used for sending data. We normally combine amplitude shift keying with phase shift keying, and we call that quadrature amplitude modulation. So, and I'm going to show you that on the next few slides. So let's start with something simple, binary phase shift keying. This is used in your cellular networks, in WiMAX, is used in Wi-Fi wireless LANs, and is actually used in Bluetooth. So it's a very common technique for representing your 1s and 0s, regardless of what type of wireless network it is. And again, it's a phase shift keying. And here I'm representing two waveforms. And if I have two waveforms and they're different, then I can distinguish between 2 bits. And so here you can see, if I come up here, I say, okay, this is a 0. And then in my next bit period, I'm going to start downwards. So I've done a 180-degree phase shift, and I say that represents a 1. So what I'm doing is every bit period, I'm changing the phase of the waveform in order to distinguish between your 1s and 0s. Again, binary phase shift keying, 1 bit per waveform. The correct terminology is 1 bit per modulation symbol, but I always like to say 1 bit per waveform because it's conceptually easier to understand. Now I can keep going. Instead of having a phase shift of 180 degrees, I can have a phase shift of 90 degrees. Now if I have a phase shift of 90 degrees, you can see therefore is that I can come up this way, I can have one coming down, one like this, and then one like this. So what I've got now is 4 different phase shifts, 4 different waveforms. And therefore, if I have 4 waveforms, then I can represent 2 bits instead of 1. Right? So I'm now sending 2 bits per modulation symbol, or 2 bits per waveform, which means I doubled your data rate. So from going from BPSK to QPSK, I can send twice as many bits in the same spectrum and double your data rate. And you say to me, well, why don't you keep going? Why don't you go to 45 degrees and have 8 waveforms and therefore 3 bits per waveform? And I can indeed do that. But it's actually better when we start getting up to higher data rates to move to a quadrature amplitude modulation. So rather than just increasing the phase differences, I'll do a combination of phase and amplitude. And to represent that, I've put it on a polar plot. And so what you can see here is the amplitude is the distance from the origin out to the dot. So each one of these represents a different amplitude. And then the phase is the distance around here from the x-axis, like this. So each one of these dots has a unique combination of phase and amplitude. And so now I have 16 dots, right? 16 unique phase and amplitude, which means I can represent 4 bits. So this bit here, this dot here, represents 0, 1, 0, 1. This dot here represents 0, 0, 0, 0. Well, then I can keep going. And then we go to something called 64 QAM. And now I've got 64 dots. And so this dot here for instance, represents 001, 011. This one next to it here, 001, 010. So I just read off these numbers here, and so I'm now able to send 6 bits per waveform. And you say to me, "Oh, Ava, why don't you keep going?" Well, there's a problem if I keep going. You'll notice here that the dots are getting closer and closer together. So if I'm operating in a noisy environment, maybe my signals are bouncing off walls and people's bodies and people are moving, etc., it's quite possible that my signal will kind of come over here. And then I have to kind of guess, is it this dot or is it this dot? And if I guess wrong, then I've got the wrong bits and I'm going to have a corrupt frame. And so I'm great as long as my signals are coming in fairly close to where this dot is. But if I move into a more difficult RF environment where I start getting errors because I'm guessing wrong as to which dot it is, then I have to go from 64 QAM back to 16 QAM. Because you can see if I got a dot coming in here, I can say, oh, it's probably this one. And then if I start getting into a more difficult RF environment and 16 QAM is giving me error, then I'll drop back to QPSK. And if that gives me error, I'll drop back to BPSK. And if BPSK gives me errors, then I'm out of coverage. I can no longer communicate with the radio because I've now got such a difficult environment, I'm not able to recover my signals at all. Now this is the picture that now brings that all together for you. So what you would have observed if, let's say you've got 802.11g radio at home, your wireless LAN is 802.11g, and you've noticed that if you're close to the access point, you can get up to high data rates. You can get up to 54 megabits per second. And as you walk away, your data rates drop to 48, to 36, to 24, all the way down to 6 megabits per second on the edge of the cell. What's happening there is that when you're close to the access point, you're able to use 64 QAM, you're able to get to the higher data rates. Your RF conditions are good, maybe you've got line of sight, you're close to the access point. As you move away or you move into more difficult RF environments, it's more difficult to recover your signal. You have to drop to 16 QAM, to QPSK, and then right out on the edge of the cell coverage, you need to drop down to BPSK, 1 bit per waveform, and at that time you'll be down at 6 megabits per second. And if you go beyond that, you'll be out of coverage of your wireless LAN and you won't be able to communicate with it. So this is what we mean by modulation. As you move around, your modulation changes. Cisco calls this rate matching. If you hear those terms, rate matching. You're matching your data rate to your RF conditions. Good RF conditions close to your access point, higher level of modulation, higher data rates, further away, lower modulation, lower data rates. And believe it or not only does the wireless LAN Wi-Fi operate that way, but the same thing is true of your cell phone and WiMAX. All of these technologies that are doing high-speed data operate in the same way. The closer you are, the better your RF conditions, the higher the data rate I can get. As I move away, my data rate drops as my RF environment deteriorates. So we've talked about modulation, and in that section I talked about time division multiple access and code division multiple access and OFDM and direct sequence spread spectrum, and so I mentioned a lot of terminology. In this next part we're going to take a look, well, what does that mean? And those things are what we call different transmission methods. So we've talked about how I represent my ones and zeros in waveforms, but we haven't talked about how I send my signals out over the air, how I actually transmit in the frequency band. And that's what we're going to talk about here when we talk about RF coding. We're going to talk about direct sequence spread spectrum, OFDM. So let's first talk a little bit about spread spectrum. So spread spectrum is a technique where I use more spectrum than I actually need to transmit the signal. And so you can see in this graph that I've spread my signal over a much wider band, but I could have transmitted it just in that narrow band. And you say, well, why would you do that? Wouldn't that use more frequency? And the answer is yes, it would. But remember that 802.11 wireless LANs were designed to operate in a noisy, interfering kind of environment. So if I spread my signal across a wider band and there's some interference in that band, then the probability of me being able to recover that signal is much higher. And so spread spectrum is a technique that was defined in the early part of 802.11 because they knew that this was a shared spectrum. And it is exactly what is suggesting in this graph, a way of spreading your signal over a much wider band when it's transmitting. There are two types of spread spectrum technique. The first one's frequency hopping spread spectrum, and Bluetooth uses that. And the second one is direct sequence spread spectrum, and this is used by 802.11b. It's also the technique used by Zigbee that we talked about earlier. Now, frequency hopping, what that does, and the name might suggest it, is it literally hops across a wide band. So it transmits on this frequency for one moment, jumps to another frequency, transmits there, hops to another frequency, transmits there. Now, the pattern that it hops in needs to be known so that the receiving side knows what frequency it should be listening to. But if it hops to a frequency that suffers some interference, it could lose that part of the signal, but then it's going to hop to another one, and then the probability is that something else isn't there, and you'll be able to get that part of the signal. So it literally hops across the frequency band, so it hops over a wider band in order to give it diversity on the frequency so it can operate in an interference-orientated environment. So direct sequence spread spectrum, used in 802.11b, is a way of applying a code to the bit stream. So I literally take your ones and zeros and apply a code. And what that does is it increases my bit rate. So let's say your traffic was at 1 megabit per second, I apply a code and you end up at 11 megabits per second. And you say, well, why do I do that? Well, because if I transmit at a higher data rate, where each of those bits is at a lower power level, what will happen is my signal will spread, like we saw in the previous slide, across the band. And because I've applied these codes, I'm transmitting many, many more bits than your original information bit. And so if I lose a few of the bits because something's interfering, I can recover from it and I can still get back to your original bit. So it's a concept of applying codes and spreading the signal over the band. Now, it's important to know that 802.11b uses direct sequence spread spectrum, but it is the older technology. And it was great, but now we're moving to ORF-DM. And this is a much more important technology to try and understand when it comes to Wi-Fi. And 802.11agn and the newer standards, AC, all support ORF-DM. So ORF-DM is simply a different technique than spread spectrum, and is a more complicated technique. Sometimes the radios therefore tend to be a little bit more expensive, but the benefit is that in the same spectrum, the same frequency channel, I can get up to higher data rates. And given the increasing demand on our wireless networks, I want to get up to the highest data rate I possibly can in the given spectrum, because that bandwidth is really needed, especially with all the video streaming that's going on over our wireless devices today. So ORF-DM, and here I'm looking at a picture of 802.11n, and what ORF-DM does is it says, oh, well, let me take a frequency band, and in this example I've got a 20 megahertz channel, and let me slice it into smaller subcarriers. And in this example, I've actually sliced it up into 64 subcarriers, 48 of which are shown here that actually carry data. And again, here I'm looking at 802.11n. Okay, so basically each one of these is going to carry a bit stream. So you can think about this as this one carrying bit 1, this one carrying bit 2, this one carrying bit 3, this one carrying bit 4, etc. So each of these individual subcarriers is going to carry data. Hence the term frequency division multiplexing. I slice up the frequencies, I divide the frequencies, and I multiplex my data onto the frequency channel, i.e. I'm sending multiple bits on different frequencies at the same time. The secret of this technology is that it's orthogonal, and you'll see here how the signals overlap with one another, and see how this signal here is a null, why this one peaks. That's the property of orthogonality. So I can literally get the signals to overlap and not interfere with each other, which means I can get lots of subcarriers really close together, and that means I can get up to super high data rates. So we've talked about direct sequence and spread spectrum, and this is orthogonal frequency division multiplexing, just different ways of transmitting over the frequency channel. So I always find people get confused when I say, yeah, the signal goes over a 20 megahertz band in the 2.4 gigahertz band. And they're like, whoa, what does that mean? So the best thing to do is to take a look at a spectrum analyzer. So that's what we're going to do now. And at the end of the demo, you should feel pretty good about what a channel bandwidth is, because I'm going to show you my 802.11 operating on a 20 megahertz channel. And we're also going to look at some different signal profiles, and you're going to see other signals operating in the 2.4 gigahertz band along with my Wi-Fi wireless LAN. In this demo, I want to take a look at one of my favorite tools, Channelizer, and what I'm going to do is I'm going to be using a wireless adapter, and I've brought up here a website of MetaGeeks, and you can see up here the different types of adapters. So I've plugged one of these adapters in, and I'm actually running Channelizer 4. So let's take a look at that now. So I've brought up the Channelizer tool, and you can see already that it's starting to pick up signals in the 2.4 gigahertz band. Now how do I know this is the 2.4 gigahertz band? See here, is displaying the different frequencies across the 2.4 gigahertz band. Down here you can see the actual networks that it's discovering, and you can see here's Avril's network. I have one access point on channel 1, and you can see I've got security of WPA2. Over here you can see I've got a second access point. Now this is an 802.11n that's operating on a 40 megahertz channel, so it's going across channel 11 as the primary and channel 7 as the secondary. So whereas this is a 20 megahertz channel, this one here is a 40 megahertz channel. This is my network operating in the 5 gigahertz band up on channel 36, and this one here, if you go across, this is actually an ad hoc network, and we'll talk about the difference between ad hoc and infrastructure later on. If I look here at the data rates, I can tell just by looking at the data rates that these are all 802.11n, because A and G only go up to 54 megabits per second and B only goes up to 11 megabits per second. So let's take a look at what these look like. I'm going to click on Avril's networks here, and we'll display those. And here you can see this is channel 1. And here you can see this is channel 7 and 11. And if you don't believe me on the channels, I can change the view here and just say, oh, rather than having frequencies displayed, let me display the channels. And now you can see. And so the main thing I wanted to point out to you here was that this is deploying on channel 1 and is using a 20 megahertz band. See how it's spreading that signal over a 20 megahertz band? Whereas up here, in the higher part of the 2.4 gigahertz band, I've got a 40 megahertz channel, so it's twice as wide, operating on channel 7 and 11. So it's added those two channels together. Now I can also here display the iMac here. I turn that one on and you can see that's deployed on channel 5, and you can see that it overlaps with my other access points. And so when you see that, you know there's going to cause interference with each other. So let me just turn the iMac off. So the other thing I wanted to show you was the kinds of signatures. Now I can tell by the square shape of these signals like this square shape here, that this is an OFDM signal. And so different radios have different signatures. And so by looking at the signatures, I can kind of tell what might be transmitting. So if I come down here a bit, here you can see the types of things. See, this is an 802.11b radio, gives me this kind of curved look to it. If I come down a bit more, here's some examples here of a cordless phone. This is an OFDM signal. This is Motorola's Canopy, and that uses an OFDM system different from 802.11. But similar signal because it's still an OFDM structure. And so different radios have different patterns. And so here again, come down a bit, I can start to see videos, etc. So I can literally profile different pieces of equipment that could be operating in my band. So if I click over here on this button here, I'm going to display what else is happening in the 2.4 gigahertz band. So you can see my two access points, but now you can see, wow, what is this thing jumping all over the place? And I could look down here at one of these profiles and say, well, gee, does it fit with one of these profiles? And so you can come down and say, well, you know, is it a cordless phone? Yeah, could it be this AV transmitter? You come down a bit more, you know, oh, you know, could it be a headset that's going on here? Now, to keep you out of suspense as to what this actually is this is actually a proprietary technology, and so this is a technology which would be very difficult to actually determine what it is based on the signatures, because this is actually proprietary and it's not a known signature. This is actually my solar power system, and I run a solar power system in my home, and it is transmitting updates as to how much energy I'm generating, and so that's what you're seeing in the band. And if I look here at my y-axis, you can see the power level that is transmitting at as to kind of the impact it's going to have on my Wi-Fi system. Remember that the way Wi-Fi operates is it's going to listen and it will only transmit if it doesn't hear any noise in the band. So let's turn off my signatures there and go back to my network table. So I just want to close that. I don't want to save the file. And again, to pick up those signals, all I've done is I've added in my wireless adapter. I'm running Channelizer 4 as my application, and I'm picking up signals in the 2.4 gigahertz band, and you can see that 802.11n uses a 20 and a 40 megahertz channel in the 2.4 gigahertz band. So the main thing here is to understand the frequency band that I'm looking at, and then that my signals actually operate across a band. In the case of Wi-Fi, that's a 20 or a 40 megahertz channel. So I hope you really found that valuable, because a lot of people really get confused between what's a channel band and what's the frequency band and what does all that mean. So play with this, take a look what's happening in the band. You can take your tool, your wireless adapter in the laptop, and walk closer to the source of interference. You're going to find those signals will get stronger. As you move away, they get weaker. So play with these tools. And again, I'm not recommending Channelizer and the Y-Spy tool. This is simply the tool that I use because it's very, very easy to use. It's simple to understand, and it's a really good tool to get yourself going. I use it a lot when I go to conferences just to explain the basics of frequency channels and channel bandwidths. So well done in getting through this section.